Good morning everyone. Today I, Manshi Kumari from BSc Chemistry Honors Final Year is going to make an audio regarding for visually impaired students of Physical Chemistry book of Pradeep Publications. Name of chapter is Physical and Molecular Structure. It's part 2 and article 5.3.2, that is electrical polarization of molecules. In this, every molecule is made up of positively charged nuclei and negatively charged electron cloud as shown in figure 5.9a. The center of positive charge coincides with the center of negative charge. Hence, when such a molecule is introduced between the two plates of an electric field, the positively charged nuclei and hence the center of positive charge is attracted towards the negative plate, whereas a negatively charged electron cloud is attracted towards a positive plate of the electric field. As a result, the molecules gets distorted as shown in figure 5.9. This is called polarization of the molecule, and the distorted molecules with positive and negative ends is called an electric dipole or dielectric. The molecules remains polarized so long as the electric field is applied, but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to the negative charge on the another. Suppose this charge is q. If d is the distance of separation between the charges, then the dipole moment of the induced dipole, called the induced dipole moment represented by mu I, will be given by mu I is equals to q into d. Evidently, the value of mu I will depend upon the nature of the molecule and the strength of the electric field. Say x, we write mu I is equals to alpha into x, where alpha is constant and is called the polarizability of the given molecule. Alpha is further found to be related to the dielectric constant d of the medium present between the plates, that is the molecules being studied. According to the equation put forward by Clausius and Mossotti, d minus 1 upon d plus 2 into m upon rho is equals to 4 by 3 pi n into alpha, where m is the molecular mass of the molecules, rho is the density of the molecules, n is Avogadro's number. Next is Clausius-Mossotti equation. Suppose an electrostatic field is applied to two plates so that they are charged. Suppose the strength of the uniform electric field produced between them is equals to E naught. Now, if a non-polar medium is placed between the plates, the strength of the electric field will be reduced to E because the induced dipole called dielectrics act in opposition to the applied field and hence partially neutralizes the charges of the plate as shown in figure 5.10. The ratio E naught upon E is called the dielectric constant D or relative permittivity of the medium. From electrostatics, it can be shown that E naught is equals to E plus 4 pi I, where I is the induced dipole moment per unit volume, that is I is equals to mu I into N, where mu I is the induced dipole moment in a single molecule and N is the number of molecules per cc. Dividing both sides of equation 4th by E and putting E naught upon E is equals to D, we get D is equals to 1 plus 4 pi I upon E, or D minus 1 into E is equals to 4 pi I. The intensity of electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plates. The electric intensity X is then made up of the following parts. First, the field strength of the charges on the plates is equals to E naught. The charges induced on the surfaces of the dielectrics in contact with the plates is equals to minus 4 pi I. Third, the charge induced on the surface of the spherical cavity is equals to plus 4 by 3 pi I. Now xi is equals to E naught plus 4 by 3 pi I minus 4 by 4 pi I. Substituting the value of E naught from equation 4th, we get xi is equals to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I is equals to E plus 4 by 3 pi I. Substituting some value of 4 pi I from equation 5th, it becomes xi is equals to E plus d minus 1 upon 3 into E is equals to 1 plus d minus 1 into 3 into E is equals to d plus 2 upon 3 into E. From it's called equation 8th, and from equation 7th and 8th, E plus 4 by 3 pi I is equals to d plus 2 upon 3 into E, or d plus 2 upon 3 minus 1 into E is equals to 4 by 3 pi I, or d minus 1 upon 3 E is equals to 4 by 3 pi I, named as equation 9th. Putting I is equals to mu I into n as already defined, mu I is equals to alpha xi, so I is equals to alpha xi into n, and xi is equals to d plus 2 upon 3 into E, so I is equals to alpha into d plus 2 upon 3 into E into n. And so equation 9 becomes d minus 1 upon 3 into E is equals to 4 by 3 pi alpha into d plus 2 upon 3 into E into n, or d minus 1 upon d plus 2 is equals to 4 by 3 pi n alpha, named as equation 10th. If rho is the density of the substance placed between the charged plates, that is of the medium between the charged plates, and m is its molecular mass, then molar mass of the substance is equals to m upon rho. If n represents Avogadro's number of molecules per unit volume, that is n is equals to capital N upon m upon rho is equals to n rho upon m, named as equation 11th. Substituting this value in equation 10th, we get d minus 1 upon d plus 2 is equals to 4 by 3 pi into n upon m into rho alpha, or d minus 1 upon d plus 2 into m upon rho is equals to 4 by 3 pi n alpha, named as equation 12th. As all quantities on the right hand side of the equation are constant, alpha being constant for a given substance independent of temperature, therefore the quantity on the left hand side of equation 12 must also be constant. Independent of temperature and depending only upon the nature of the molecule, this quantity is called molar polarization and is represented by P. Further, as the applied field produces an induced charge in the molecule by relative displacement or distortion of electrons and nuclei, P is often called induced or distortion polarization and is represented by Pi or Pd. Thus, Pi or Pd is equals to d minus 1 upon d plus 2 into m upon rho, named as equation 13th. Induced molar polarization is defined as the amount of polarization produced in 1 mole of the substance when placed between the plates of an electric field of unit strength. From equation 13, it is evident that the unit of Pi will be same as that of m upon rho, that is molar volume. Hence, Pi is usually expressed in centimeter cube per mole. Equation 13, giving the relationship between dielectric constant and polarizability, was first derived by Mosotti in 1850 and Clausius in 1879 and is called Mosotti-Clausius equation. Now next article is effect of temperature on polarization. Using equation 13, the value of molar polarization have been determined for a number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization values for some other substances such as HCl, CHCl3, C6H5NO2, and CH3Cl, do not come out to be constant but decrease with the increase of temperature. This observation has been on the basis of measurement of dipole moment and the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, etc., their centers of positive and negative charges do not coincide with each other. Thus, they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by the molecules is called permanent dipole moment. In the absence of electric field, these permanent dipoles are oriented in a random manner due to thermal agitation as shown in figure 5.11. However, in the presence of electric field, two disturbing effects takes place. These are: first, the electric field will tend to rotate and orient these dipoles in the direction of the field. Second, the electric field will tend to polarize the molecules. Now, if the molecules were stationary, the dipoles would have been oriented perfectly parallel to the electric field, that is, at the right angles to the plate of electric field. However, due to thermal agitation, they take a position in between that of original state and the perfectly parallel state as shown in figure 5.12 for any one permanent dipole. Thus, in case of molecules possessing permanent dipoles, the right hand side of equation 13 will give the total polarization P1, which will be the sum of induced polarization Pi and the orientation molar polarization Po. That is, P1 is equals to d minus 1 upon d plus 2 into m upon rho is equals to Pi plus Po. As mentioned earlier, the induced polarization is given by Clausius-Mosothy equation with Pi is equals to 4 by 3 pi into n into alpha. And as equation 15th, the orientation molar polarization is given by the equation put forward by Debye, that is PO is equals to 4 by 3 pi n into mu square upon 3 kt, equation 16, where mu is the permanent dipole moment of the molecule, k is the Boltzmann constant which is equals to r upon n, and T is the temperature. Substituting the values of P1 and Pi and Po from equations 15 and 16 in the equation 14th, we get P1 is equals to d minus 1 upon d plus 2 into m upon rho is equals to 4 by 3 pi n into alpha plus 4 by 3 pi n into mu square upon 3 kt, named as equation 17th. Now next article is measurement of dipole moment. Its first method is vapor temperature method. The above equation can be written in the form of Pi is equals P1 is equals to A plus B upon T, where A is equals to 4 by 3 pi n into alpha and B is equals to 4 pi n mu square upon 9k are constant for the given substance. This equation is primarily applicable to gases and vapors. Thus, if P1 is plotted against 1 by T, a straight line graph will be obtained if the molecules possessed permanent dipoles. The slope of the plot will be given by B is equals to 4 pi n mu square upon 9k. Equation 19. From this equation, the permanent dipole moment mu of the molecule can be calculated as all other quantities are constants whose values are known. Solving equation 19th by putting the values of the various constants, we get mu is equals to 0.0218 under the root b into 10 ki power minus 18. The straight line plots for a few substances with and without permanent dipoles, that is polar and non-polar molecules, are shown in figure 5.13. It may be seen that whereas Pt varies with temperature for HCl, CHCl3, etc., possessing permanent dipoles, there is no effect of temperature on substances like CH4, CCl4, etc., which do not have permanent dipoles and hence possesses only induced molar polarization. Now, methods of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equals to d minus 1 upon d plus 2 m upon rho is equals to a plus b upon t, equation 20. Whereas a and b are constant with b is equals to 4 pi n mu square upon 9k. Thus, the experiment involves the determination of the dielectric constant D and the density rho at different temperature T. The value of Pt are then calculated Values of Pt are then calculated and plotted against 1 by T. If Pt is found to vary linearly with 1 by T, the substance possesses a permanent dipole moment and the value of dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment, that is, it is non-polar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in a vacuum between the plates CO and then measuring the capacity of the same condenser when filled with the given substance C. The dielectric constant of the given substance is then given by D is equals to C upon C naught, equation 21. Second is the refraction method. According to Clausius-Mosothy equation, the induced or distortion molar polarization Pi or Pd of the molecules is given by Pi or Pd is equals to d minus 1 upon d plus 2 into m upon rho is equals to 4 by 3 pi n into alpha, equation 22. As the dielectric constant is a pure number, molar polarization P is simply molar volume of the material. Further, it has already been explained that is independent of the temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell in 1881 that the dielectric constant of a substance is related to its refractive index for light of long wavelength according to equation D is equals to n infinity square, equation 23. Substituting this value in equation 22 above, we get Pd is equals to n infinity square minus 1 upon n infinity square plus 2 into m upon rho is equals to 4 by 3 pi n into alpha, equation 24. However, n infinity square can't be found by extrapolation to infinite wavelength. The values of the refractive indices measured with visible light. This is because visible light can displace only electrons, whereas the positively charged nuclei remain unaffected. Thus, the distortion polarization can be considered to be the sum of electron polarization Pe and atom polarization Pa. That is, Pd is equals to Pe plus Pa. To find values of Pd, it is therefore necessary to measure the refractive index using infrared rays because they can displace the heavy atomic nuclei as well as the electrons, but measurement of refractive index with infrared radiations is difficult. Hence, the problem is solved by finding electron polarization by measuring the refractive index n using visible light d line, that is Pe is equals to n square minus 1 upon n square plus 2 into m upon rho. As an approximation, 5% of this value is added to it to account for Pa to get the total value of Pd, that is Pd is equals to Pe plus Pa, which is 5% of Pe. Then, as before, total polarization Pt of a molecule possessing a permanent dipole moment is the sum of the two terms, the first called distortion polarization Pd and the second called the orientation polarization Po. Due to permanent moment possessed by the molecules, hence we can write Pt is equals to Pd plus Po, equation 26. Putting the value of PO from Debye equation, which is PO is equals to 4 by 3 pi n into mu square upon 3 kt. Equation fifth becomes PT is equals to PD plus 4 by 3 pi n into mu square upon 3 kt. Equation 28. Putting the values of the constant and simplifying, we get mu is equals to 0.0128 into under the root pt minus pd into t. Pt can be determined by finding the dielectric constant of the vapor at a temperature T, and Pt can be found either by measuring the refractive index using infrared radiation or by approximation method explained above. This method is simpler than the temperature method because it involves the measurement only at one temperature. Third is the dilute solution method. Equation 20 is applicable to gases and vapors only. For substances which are not gaseous or which can't be converted into vapors, the following procedure is followed. First, a dilute solution of the given substance is prepared in a non-polar solvent such as benzene, CCl4, CS2, etc. The density and dielectric constant of the solution are determined at various temperatures. Second, at each temperature, the molar polarization of the solution PS is calculated using the relation PS is equals to D minus 1 upon D plus 2 into x1 m1 plus x2 m2 upon rho, equation number 30, where x1 and x2 are the mole fractions of the solvent and the solute in the solution. M1 and M2 are the respective molecular masses, and rho is the density of the solution. Third, the molar polarization of the solution is related to the molar polarization of the solvent x1 and that of solute x2 as PS is equals to x1 p1 plus x2 p2. Thus, knowing the values of x1, x2 and p1, the value of p2, that is molar polarization of the solute substance being studied, can be calculated. Fourth, the value of P2 obtained at different temperature are plotted against 1 by T. The value of mu is then calculated from the slope of the line as explained earlier. Now the next article is dipole moment and chemical constitution, that is the applications of dipole moment. The knowledge of the dipole moment of a molecule can be applied in a number of ways to study its chemical constitution. A few important applications of a dipole moment are briefly described below. First, in comparing the relative polarities of the molecules. For example, the dipole moments of HF, HCl, HBr, HI are 2, 1.03, 0.78, and 0.38 dB respectively. This shows that the polar character of the molecules decreases as we move from HF to HI. Second, in calculating the percentage ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 D. If the bond were 100% ionic, each end would acquire full 1 unit charge, that is 4.8 into 10 ki power minus 10 ESU. The bond distance in HCl is taken to be 1.275 angstrom, that is 1.275 into 10 ki power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been 4.8 into 10 ki power minus 10 into 1.275 into 10 ki power minus 8 ESU centimeter, which is equals to 6.11 dB. Actual value of dipole moment of HCl is equals to 1.03 D. So percentage ionic character of HCl bond is equals to 1.03 upon 6.11 into 100, that is equals to 17% approx. Third, in predicting the geometry or shapes of the molecules. The fact that the dipole moment is a vector quantity and that a particular bond has almost a constant value of bond moment is very useful in predicting the shapes of molecules. A few cases are described below. A. Diatomic molecules. A diatomic molecule is always linear, irrespective of its dipole moment. B. Triatomic molecules. In triatomic molecules of the type AB2, there are two possibilities. First, the dipole moment of the molecule may be zero, that is in case of CO2 and CS2. This shows that as in these molecules, one bond moment is equal and opposite to other, hence the molecules must be linear as shown below. Second, the molecules may have a definite value of dipole moment, that is mu for H2O is equals to 1.84 d, mu for SO2 is equals to 1.63 d. Obviously, in these cases, the possibility of linear shape is ruled out. The two bonds must have a definite angle between them, which can be calculated if we know the bond moments as discussed earlier in section 5.3.1. For example, the bond moment for HO is 1.6 d. The bond angle is calculated to be nearly 105 degree. Thus, H2O may be represented as shown in figure 5.14. Such molecules are called bent molecules and the shape is called V shape. C. Tetraatomic molecules. In tetraatomic molecules of the type AB3, the two simple possibilities are: the first one is the dipole moment of the molecules may be zero. Example that in BF3, in such a case, all the four atoms must be in one plane and the angles between the bonds must be equal, that is in BF3 shown in figure 5.15. Such a shape is called planar trigonal. Second, the molecules may have some definite value of dipole, that is NH3, PF3, PCl3. This indicates that one atom lies out of the plane of the rest of the atoms. For example, the molecules of NH3 may be represented. Such a shape is called pyramid shape. D. Pentaatomic molecules. The pentaatomic molecules of the type AB4, which we commonly come across, are CH4, CCl4, SiCl4, SnCl4, etc. The dipole moments of all these molecules is found to be zero. This is possible only if these molecules have a symmetrical or regular geometry so that the different bond moments cancel out each other. The experimental facts confirms that these molecules have tetrahedral shape as represented below. Fourth, in differentiating the cis and trans isomers. The cis and trans isomers can be represented as shown in figure. It is clear that the trans form will be non-polar, that is will have zero dipole moment, whereas cis form will be polar, that is will have definite dipole moment. For example, in case of dichloroethylene, putting X is equals to Cl, cis form has been found to have a dipole moment of 1.9 d, while the trans form is found to have a zero dipole moment. Fifth, in differentiating O, M, and P isomers. As benzene is regular hexagon and its dipole moment is zero, therefore substituting two atoms or groups in the ortho, meta, and para position, the di-substituted derivatives will have different dipole moment for the ortho, meta, and para isomers as shown below in figure 5.18. Obviously, para will have zero dipole moment and meta will have less dipole moment than ortho. Sixth, in supporting the possibility of resonating structures. For example, the nitrous oxide molecules N2O has a small value of dipole moment, that is 0.17 d. If the molecules is supposed to have any one of the following two structure, the dipole moment should be high. This confirms that N2O molecules is a resonance hybrid of the structures first and second. Thank you so much.